determine the eigenvalues and the corresponding eigenvectors of the following matrix. I'm going to ask you to pause the video, write the question down, and then go ahead and work it out. Okay, you have done it. What did you get? Let's work it out together. Now, remember, the discussion behind this is that if you have the matrix A multiplied by its eigenvector x, now remember that eigen is German for own. So the matrix A multiplied by its eigenvector x is equal to, instead of using the whole matrix, you use the value of the matrix, its own value, which is eigenvalue multiplied by the eigenvector of the matrix. So remember, this is the matrix, this is the eigenvector, this x as well, and you have the eigenvalue. Alright? Lambda. Now if you should put everything on one side and equate them to 0, you say ax minus lambda x equals 0. You factor out the x, you have x times a minus lambda equals 0. Now if you write everything so that they take the shape that they would take, well, let's put x on the right hand side first, because you would want the 2 by 2 on the left and the 2 by 1 matrix on the right. So a minus lambda x equals 0. Now writing these out in the general shape, not necessarily this particular one, A would be a matrix, 2 by 2 matrix, since we're dealing with 2 by 2 matrices here, A, B, C, D, minus lambda, which is a number, times x, let's put this here, x would be x, y, equals 0. But guess what now? You cannot have a matrix minus a single number. So you're going to have to change that number to the form of the matrix. So here, lambda must be multiplied by the unit matrix 1001. So the unit matrix, sometimes called the identity matrix, it has a name I. So you must put I here. Lambda I x. Alright? So here now, let's use that argument on this. You have 2, 2, 1, 3, 2, 2, 1, 3, minus, oh, we haven't finished with the discussion. Let me continue the discussion. We haven't really finished with it yet. Now, if you have this situation, remember, when you have a number multiplied by 0, you get 0. Or if you have the matrix multiplied by 0, the null matrix, you get 0. So this is suggesting that the eigenvector is a null matrix, but that's not really so. Right? You see A minus lambda I x. In order to find x, you would have to say x equals 0 over A minus lambda I. But the thing is, you can't do that directly with matrices. You can't just divide like that with matrices. What you have to do is say a minus lambda I times the inverse of a minus lambda I times x equals 0 times the inverse of a. Let me put to the negative 1 for inverse a minus lambda I inverse. Now if you could do this, it would mean that x, the eigenvector, is always 0, but that's not so. So therefore you should not be able to find the inverse of a minus lambda I. So therefore a minus lambda I is a, and remember the name, the type of matrix that you cannot find the inverse of, it is a singular matrix, and that means a minus lambda I, the modulus of it is equal to 0, or the determinant, I should say, of a minus lambda I is 0. So let's find a minus lambda I and equate the determinant to 0. So here now we have, if we have a minus lambda I, what you'll be saying is that 2, 2, 1, 3 minus lambda times 1, 0, 0, 1. And then if you find the determinant of this, you get 0, right? Because it's a singular matrix. See that? Now, we're going to calculate to find out what lambda would be equal to. So now, you have 2, 2, 1, 3 minus, if you multiply lambda by the unit matrix, you have lambda 0, 0, lambda. The determinant of that is 0, right? Determinant is 0. And then if we subtract the corresponding terms, determinant of 2 minus lambda, 2 minus 0, 1 minus 0, 3 minus lambda. Alright, you see that? Equals 0. You could rewrite this and say 2 minus lambda, 2, 1, 3 minus lambda, and the determinant of that equals 0. So let us calculate the determinant to find out what it is. Remember your AD minus BC method. Don't forget that method, right? So it's 2 minus lambda times 3 minus lambda minus 2 by 1 equals 0. Alright? So, having that, we multiply out 2, 3, 6. 2 by negative lambda is minus 2 lambda. Negative lambda by 3 is minus 3 lambda. Negative lambda by negative lambda is plus lambda squared. Minus 2 equals 0. So you have lambda squared. Negative 2 minus 3 is minus 5 lambda. 6 minus 2 is minus 4 equals 0. They call this the characteristic equation. So, what? Oh, plus 4, because 6 minus 2 is plus 4 equals 0. So, let's solve this. Can we do it by factorization? Yeah. If we multiply a by c, this is in the form a, well, it's not x squared anymore. For this, it is a lambda squared plus b lambda plus c equals 0. So if you multiply a by c, a times c, in this case is 1 lambda squared, so it's 1 times 4 equals 4. And then we must find two numbers that multiply to give AC and to give B. Which two numbers multiply to give 4 and add to give negative 5? Well, we could try 4 and 1. Aha! Negative 4 times negative 1 is positive 4. And negative 4 plus negative 1, same as negative 4 minus 1 is negative 5. So these two numbers will work. Just a matter of factorization, right? If you don't remember the factorization, but you remember the formula, you could solve, and you're going to have lambda plus 4 by lambda plus 1 equals 0. So lambda would be, no, it's not 4 and 1. Alright, let me finish this first and then talk about other methods if you don't remember how to solve this using factorization. You're going to split the negative 5 into negative 4 and negative 1. So you have lambda squared minus 4 lambda minus lambda plus 4 equals 0. You see, it's the same equation, you know. It's just that you, instead of negative 5 lambda here, you have negative 4 lambda minus lambda, which is the same as negative 5 lambda, right? Factorize this in group now. Lambda, then I have lambda minus 4 minus 1, lambda minus 4 equals 0. So lambda equals, no, lambda minus 1, let me put the minus 4 first, lambda minus 4, factor it out, open bracket, lambda minus 1 equals 0. So what you're going to get is lambda equal 4 and lambda equal 1. Let's call this lambda 1 and lambda 2. Alright? So these are the values you'll get. These are the eigenvalues. Now, we were asked to also find the corresponding eigenvectors. So we're going to put x back in it now. Remember, we have a minus lambda I times x equals 0. But the thing is now, after you find these, you're going to put in an x and a y for each lambda, right? So this will become a, what is it again? 2, 2, 1, 3. The matrix A is 2, 2, 1, 3 minus lambda I, which is 1, 0, 0, 1 times x would be a column matrix xy. Remember, the vector is represented as a column matrix. The x is at the top, shows the horizontal displacement, and the y at the bottom shows the vertical displacement of the vector. That's equal to 0, 0. The 0 is really a vector. It's all vectors here. So, rewriting this part, we have 2, 2, 1, 3 minus lambda 0, 0 lambda, after you multiply the lambda by the identity matrix 1, 0, 0, 1, alright, times x, y equals 0, 0. Now, as I was saying before, we found lambda 1 equals 4 and lambda 2 equals 5. If you should solve it using the quadratic formula, you would get the same lambdas here, so that we use factorization. Or if you should use completing the square and solve it, this is what we would, these are the roots that we would get, right? It's just that we use factorization instead. Alright, now there were two lambdas. Lambda 1 equal 4. We have run out of scrolling space, so let us draw a vertical line going up and work on the right hand side of this line. Let me just draw a line under the working here. Alright, so let's continue here. Now, the thing is, for lambda 1 equal 4. So, while lambda 1 equal 4, that means one of the eigenvalues that we got is 4. When that happens, we're going to substitute the value of that lambda, right? Going to substitute it here. Now we have 2213 minus lambda 0 0 lambda, so it's going to be 2213 minus, it is 4, so it's 4004. Instead of writing lambda 0 0 lambda, we know lambda is 4 here, so we write 4004, alright, times xy equals 0 0. That times xy equals 0 0. Alright, subtract these. 2 minus 4 is negative 2. Then you have 2 minus 0 is 2, 1 minus 0 is 1, and 3 minus 4 going to be negative 1, right? And xy equals 0 0. Alright, so let's see how this goes. Multiply out the matrices. Negative 2 by x is negative 2x. Let me do a little thing here, give me 1 second. Alright. So negative 2x plus 2y equals 0. I have 1x, which is x, minus 1y equals 0. We have two equations here. Let's fix this one up. This, if we divide both sides of the top equation by negative 2, so call this equation 1 and this equation 2. Divide equation 1 by negative 2. We have negative 2x over negative 2 is x. 2y over negative 2 is minus y equals 0. So we see that equation 1 and equation 2 amount to the same thing. Now when you equate them, x minus y equals 0, so therefore x equals y. The eigenvector will change, will take this shape. Since x is equal to y, the simplest eigenvector you use is 1 1. Alright? 2 2 can work because 2 is equal to 2. 3 3 can also work because 3 is equal to 3, and so on. But in this case, 1 1 is the simplest of them. Alright? So when the eigenvalue is 4, when lambda equals 4, well, I should really, let me use big X because it's the name of a matrix. X equals 1 1, alright? Since it's the name of a matrix, I really should use big X, and I used small x before. Alright, now for lambda to equal, what was it again? lambda 2 equal 1. What happened? Now we're going to use back this equation, but instead of put 4, we put 1. It's really this general equation. 2213 minus going to be 2213 minus, it was lambda 0, 0 lambda, but since lambda is 1, I'm going to change the lambdas here to 1, 1 0 0 1. Alright, so that's what we have there. Times, oh my, times, and we have the x, y equals 0 0. By the way, I had labeled this lambda 1. Label these x, y, x1, y1 then. Since we have lambda 1, because each lambda will have its own x, right? So x1 equal y1. Now, for lambda 2 equal 1, we're going, since we call this lambda 2, we're going to work with the name x2, y2 equals 0 0, right? So here we're going to have 2 minus 1, 2 minus 0, 1 minus 0, 3 minus 1. x2, y2 equals 0 0. So here now, 2 minus 1 is 1, 2 minus 0 is 2, 1 minus 0 is 1, 3 minus 1 is 2, times x2, y2 equals 0 0, okay. Then we multiply the thing there, we multiply the matrices. Let me draw a line up because we run out of scrolling space again. Let's continue working on the right hand side of this line. So here, when you multiply the matrices, you're going to have 1x2 plus 2y2 equals 0. So x2 plus 2y2 equals 0. That's essentially what you will get. x2 plus 2y2 equals 0. And here, multiply these, get x2 plus 2y2 equals 0 again. So you have x2 plus 2y2 equals 0. So they are the same thing. Equation 1 and 2 for this part is the same. They are the same, so let's use just one of them. So what you have then is that x2 is equal to negative 2y2 when you add 2, when you subtract 2y2 from both sides, right? Now, what we have here is x equals 2y2. Now, if we put in a value for y2, we can find out what x is. Simple value. We can change it later and simplify it down if we can do that. So, if we say let y2 equal 1, then x2 will be negative 2 times 1, which is negative 2, right? So what we can do is make the matrix where x2 is negative 2, y2 is 1. I choose y2 as 1 to make it simpler. Right? It's the same thing as negative 4, 2, or negative is 2 times negative 6, 3, and so on and so forth. But here, x2 is negative 2y2. So whatever y2 is, multiply by negative 2 and I get x2. That is the eigenvector. So for lambda 2 equal 1, alright, let me just write down a conclusion here. When lambda is 4, x equal 1, 1. When lambda equal 4, x equal 1, 1. And when lambda equal, was it 1 again? Was it, yeah, for lambda, this would be lambda 2 now. When lambda equal 1, then x equal, and we got negative 2, 1. So therefore, when the eigenvalue is 4, the eigenvector is 1, 1. When the eigenvalue is 1, the eigenvector is negative 2, 1. That's what you're saying. Alright? So, I'll see you in the next video then.